Welcome folks to lecture 10, CS621C. We're still talking about MIPS and how you translate C to MIPS. Today we're going to talk about, how to translate procedure calls, okay, into MIPS. A little bit more complicated than just doing the standard arithmetic stuff. So, delightful article in, I guess it was a Technology Review, which was, they did a cellular automata simulation of traffic. And it turns out that there's three kinds of traffic. This article pointed out really kind of neat. I hadn't realized this. There's traffic that could be prevented, traffic that is unavoidable, and there's something in the middle which is kind of fuzzy, which is you can optimize for and prevent it if you can. So what this shows is on the right, the traffic, I guess, is, it's hard to read these charts, but all the early traffic here, which were the preventable traffics, were removed if you did the following thing. If you had your cars talk to each other, share the information about traffic jams, and then if you're in a traffic jam, the moment the traffic jam is cleared, you basically compress the distances between your car and the car ahead of you. So you really rush to get out of the traffic jam, try to bleed it out as fast as possible. And if you know about traffic jam coming up, you slow down it well in advance. So you're still moving forward, but you don't ever come to a stop. So you're kind of having fewer cars come into the traffic jam, and then as soon as you're in the traffic jam, you get out of it as fast as you can, if that makes sense. And that can dissolve traffic that's in the bottom right part in this simulation versus what happens in real life. It's very complicated how traffic works, but it's kind of neat that if you could just pass information about the speed and location of traffic jams, and then here's the missing piece that they didn't mention in the article, you have to have the speed of your car controlled by the computer. In that, it will accelerate you out of it so that you'll know you just keep steering, but it'll accelerate you out of it. It will automate the process of clearing these traffic jams up, which is kind of cool. And I do drive sometimes and I hit traffic jams, so it's kind of neat that I'm relevant to that. But please do read this. It's a really kind of interesting point. And I got an email from a fan in Miami who doesn't want to share his name, but hello to a fan in Miami who's watching, and you know who you are. We'll call her L. Simpson. No, that's too much information. We'll call her Lisa S. So just for privacy reasons. All right. What we've seen so far is we've seen now the three types of instructions, down to only three different types. And those of you who are going to be building hardware to do that are really happy because that's just great. There's only three different kinds of exceptional cases, and the one thing that's common is the opcode, as Chris pointed out on last Wednesday, I believe. The opcode is a starting point for all of them, and that lets you know which one of these three types it is. The opcode tells you. That's pretty cool. We learned about using on Friday, you learned about using PC addressing for branches to save you, to kind of basically optimize your bits in the immediate fields for the branches as well. And also, we talk about jumps using absolute addressing and how to save some more bits as well. So we can jump pretty far with our jumps, and we can jump pretty far with our branches as well as we can. That's kind of cool. So today we're talking about how do we take this C code, which is a normal, boring, standard C code you might learn the first day of learning C. Here are 4 local variables, and here's a multiplication call to j and k, and all multiply is literally just multiply. It's just j times k, but it's doing it by adding up product, the multiplicand, the first argument, multiplier times. So when you call this, multiplier has to be an integer, and it is, so it actually works. It also has to be a positive integer. So anyway, there's some assumptions on this guy, but this is just multiply, right? So I equals j times k, and then m equals I times I. Simple little code. But what has to be kept track of? Let's think about this. What makes this strange and hard moving to MIPS? Yeah, sure. Rohan.
Yeah.
Haha. I'm learning names. Go ahead.
You have to remember any registers in main.
Forget registers now. Remember what? Tell me registers. Yeah. Remember registers? You have to remember registers.
Yeah, when you call mount, you have to kind of somehow save the registers that you had before.
Right. Right. See, there might have been registers you had, and so I'm over here in main, and I'm playing with some expressions, blah, blah, blah. That's what the 3 dots are before the call to mult. I got the whole thing. The whole word is filled with all my S's are filled with stuff, and my T's are filled with stuff. I call mult. What's the question? You have to know and maybe understand what's going to be preserved after that call, or do I have to do something to the guys that are there, or do I have to do something? All that is complicated, and somehow you have to remember how to get back to the line after that. Right? So I have to go down to mult, which might be a different place in my code. That's a jump. I'm jumping over to mult, but how do I know how to get back so that I can now start the next line and there's also one more piece. How about this equal sign? How does mult give me an answer back? I jump over here to another piece of code, which is mult. How does mult do a computation? And then what's the agreement with how mult is going to give me back the value that's going to be across the equal sign? Does that make sense? So a couple things to keep track of. So here's this is really cool. This lecture and the next lecture are really cool, but there's a lot of new things. So I'm going to try to go at a reasonable pace to get through it all, but also stopping for questions as much as possible. So I'm going to teach you right now, you know about the local variables and the S guys. Here are the pieces that work. And all of a sudden you're saying, wow, this is lifting the hood way more. The hood has gone from kind of like, I don't know, 20% open to like 80% open in terms of how this stuff works. Look at this. I now know there are 4 dedicated registers to procedure calls. The first question it must be, what's the first question? If there's only 4, what happens if a C code that has more? We'll talk about that in a moment. Return address, that's just telling you probably how to get back. So that's going to remember how to get back to where you called from. So RA is going to be where you started from to call the guy. Return values, there's V0, V1. Well, if these guys are functions, why do you have 2 of them? Anybody have a sense of why you have 2 of them? So oh, no, it could be there. It could be value and address, but no. A value is just, you don't want to go to memory, so you don't want to have an address there. You want to keep them both as registers. So why would you ever have 2? You only have either 0 for a void or 1, right? You know, if it's an int or a car. Are there any times you have values that are actually 64 bits wide? Yeah, back. Doubles. Yeah, if you want to return a double, you store it in V0 and V1. It stores it across those 2 pieces. Okay? Good stuff. So here we are. Here's the simplest guy. Here's the simplest C code ever. It's like, why are you even making this a function? Sum takes 2 integers, x and y, returns the sum of them. Yeah, why are you calling a procedure for that? Just put the plus in the middle of the code. But this is an example of this, okay? So sum of A and B is going to return, obviously, A plus B. You know this fact, but this is hitting it over the head again, that all of MIPS, from stored program concept, all of MIPS lives in memory, and each of them have their own addresses. So this is the code that this looked like. And you might not have realized, by the way, that sum and all your subroutines might live very far away from each other. Do you guys know that? I don't know, maybe you did. Okay. So sum lives over here in the high-rise houses, the gated community of the 2000 areas, but we're over here living in apartment level because we're students, apartment level living in the 1000 series. I'm kind of making a joke that different places of memory have different... Okay, no, it's not working so well. Note to Dan, kill the joke about the housing situation. All right, so I'm in here in Maine, and I've got what? I told you that A0 through A3 are how you pass information in. So that means when I go to sum's going to assume that all of its arguments, starting from left to right, live in a 0, 1, 2, and 3. So let's try it. So that means when sum is alive, which is down in sum, that A0 and A1 have the 2 arguments stored in them. So what I mean is I can't just say, here's sum. I have to set up the world before I move to sum with my jump here. So here's something that may be hard to wrap your head around, but maybe this is the point where it's really becoming explicit for you. The difference between C and MIPS fundamentally is, in MIPS, there's just one guy active at one time. It is the program counter. It's that local instruction. And anything that you've kind of assumed you get for free in C, which is when you make a function call, you come back to the line after the function, has to be done explicitly at the assembler level. Does that make sense? Like all the niceties of, well, I was over here and I called sum, and then I called somebody else, and it remembered where I was, and went down to sum, and then it finished it, and they came back to the line right after the call to sum, right, all those things. And maybe the call to sum has 2 sub-arguments. What if it's sum of foo of 1, 2, 3, and bar of 1, 2, 3. And foo 1, 2, 3 is an argument to sum, and bar of 1, 2, 3 is another call to another procedure, which the return value is the second argument to sum. How does that work? You say, well, see, it just works, right? You first call, you do your, like in Scheme, you have to do your evaluation, applicative order evaluation. So you say, all right, I'm over here, I do the foo of 1, 2, 3, that's my first argument, I do the bar of 1, 2, 3, I get the second argument, then I call sum on that, and it just works, right? To be able to figure out how to do the mapping. Yeah? Yes. I probably need a line above 2000 to make sure I don't just run into that. That's right, it's just true. But the whole point of what I'm trying to say is, in MIPS and in all assembler, I am just one guy. All of the context that you got for free, you have to do manually. So that's why we're kind of teaching you how we do this. So I have to literally, I can't just call sum. I've got to set up A0 and A1 so that when I move over, when I jump and just globally jump to sum starts up waking up saying, okay, A0 and A1 have some values and I can now do some work. Question?
Sum is being used as a label here, right?
Sum is a label, that's correct.
So, if I use T0, T1 instead of A0, A1, what's the difference?
Aha, great question. Could sum effectively do something in T0, T1 rather than A0, A1? There's something called procedure calling conventions. And you want to have the same convention. And here's the reason. You may know why you have a convention. Why does it even matter? It is true that I could set this up to be set up T0 and T1 with the two arguments, and then sum could add on T0, T1. Why does it matter that we all agree on the same convention? Rohan.
If you wanted to call sum from some other procedure, it should also know where the argument should be put.
That's right. So it might be called from other places, but it's always still me. I'm still the guy in theory doing that. Is there anybody else who realizes that there might be somebody else calling it, or somebody else might be writing sum for me? Anybody ever heard of libraries that you include? Like math.h and some other things? Like square root and some other things that are built in? I didn't write that. There's some assumption when I link in the object file for the libmath or libm.a, that file, that object code in there, there's some assumption. That's all I'm literally doing is linking in assembler. Right? It's actually machine language because ones and zeros, but we'll see the mapping. You're kind of seeing that there's mappings from assembler to the ones and zeros of the machine code. There's some assumption what it's doing, and we have to play by the same rules. So we have to have these register calling conventions when I have procedure calls. Otherwise, I can't just plug into that. So by always knowing that sum is going to always have the first and the second argument in A0, A1, now it plays nice together. Okay? Good. Yes, question.
What happens if you call a function that you wrote inside another function you wrote?
Ah, it's great. Can you table that question? That's awesome. That's a great question. The question was, what happens if I'm in sum and I call somebody else? That's exactly, you're a plant. That's exactly 3 slides up. So let's save that one for there. Yes, question.
On Friday, we talked about how the label for the jump would have, I think, 28 word addressing, so it's like 256 megabytes. And you said that that wasn't a problem because the programs themselves aren't that big.
So,
If you're linking all the libraries and you're trying to access those, then wouldn't you need like more?
yes. So it isn't about the label and those 28 bits. You can only jump 20. I mean, the jump has a whole way you do it where you take the 26 bits, you get the 2 more, the 28, and then you grab the 4 high-end bits from the local PC, and that gives you a jump in a range of 1 to the 16th of the whole space. So you take your 4 GB RAM, 4 GB of virtual address space, you divide it by 16, which is those 4 bits you don't get, and you can jump to now 256 MB of that range. That's the idea of that. So that's exactly right. You do multiple jumps, or we're going to see this thing called JR. That's on this slide. The answer is on this slide, which is you store the answer in a register, and you go jump JR to the register. It's a cleaner way of doing that, okay? So one of the things you'll see, so what am I doing here? Let's go back to the code. I'm first setting up A0 and A1, and you know this add is essentially like a copy, right? Or a copy of the value from S0 to A0 and S1 to A1. So I'm taking A and B, which were local variables stored in S0 and S1, copying them to A0 and A1 to set up the thing. Then I say add I, what's this about? Watch this. Add I RA 0, 10, 16. This is another word for something we call load immediate, which is take the immediate 10, 16, which happens to be where I'm going to after the jump, putting it in $RA. That's setting it up so that it knows where to go back to. It's like the return address. It's like the return address. Oh wait, it's called return address. So it's where you have to go back to. It's the address of where you return. And then I say jump to sum. I literally, it's a matter of trust. It's like I had control of the PC. I don't write it explicitly, but it's all mine, right? I'm still in my code, and I say jump, and I just hope that someday it comes back to me. And that's the trust thing. It really is. It's like raising a kid. You just hope that you raise a good kid and they go off and do good things in the world. It's like, go ahead, here's jump, and please come back with the answer. Where? V0. The assumption is that it's going to be in V0. So guess what? Sum plays nice. Sum does the right thing. Looks at the A's, stuffs the V's. This is the shortest procedure in assembly you'll ever have, which is do one thing, and then $RA, which is jump register wherever this RA is. But guess what? I stored it to be 1016, and guess what? Blink, control now passes to below my jump, and I'm good. And we keep going. Everything works. It's as simple as it can be, but it also works. It's beautiful. It's very, very elegant. I trusted it, and then they came back. What is it? If you love something, let it go, and if it comes back, right? So this is like that. Same thing. Okay. Yes. Question.
So
Correct. 2000 just before is the address of that stuff. That was this previous slide saying that these things are addresses, and that's what that was my argument of like the gated community of where sum lives. Yes. Okay? And I could have written some in my 1.c file, or it could be something I linked in from you or from a library. It doesn't matter. It's just somewhere that's different from 1016 area. Okay? Other questions? Windows all right? Yes, right there. Rowan again.
Do you always know the addresses of your...
I love it. Do I always know where I'm going back to? How did I know I was on line 1008 and I need to go back to 1016? Is there something about that bothers you? That you have to know where you live? I don't like that. Does that bother anybody else? Where it's kind of like hard coding something. Whenever you're thinking of hard coding a constant in there, say don't do that. That's a style thing. You want to put that in a pound define and then reference the pound define so you can reference it other places. We talked about that with the for loop before. You never want to have a hard-coded value in there if you can help it. You always want to put it up in there in a params file or some constant thing and re-reference that. So I don't like the fact that 1016 is killing me because I don't like it. And it means that if I take my code and slide it up, you're like, what do you mean slide it up? Sometimes you have to like slide your code around. We'll see this. We'll slide our code around. And if I slide the code around, this thing breaks. Right? It's fragile. I've created a system that I can't have my code live in a different place. It has to live exactly there. Or I have to remember that 1016 should be modified, which is another annoying thing. So I don't like that. I want a system that, and that's the other slides, I'm leading up to the solution. I want something else to give me. Yeah, question. Program counter is a register. It's like the 30th, we talked about before, the 33rd register. It's something I can't get access to, but it's telling me it's going to have the value 1012, 1016. It's the guy affected by the JR. I can't touch it, though. So far, I can't touch it. I can touch it by saying JR, which is going to move me to some place, but I can't officially touch it other than with the JR. So far. Question?
What if Jump just said, whatever position I'm at now, store the address, whatever comes after it?
I love it. What if there were, rather than Jump, there was something like better than that remembered where I am, peeked into the PC, grabbed it, and then set, right? That would be beautiful. And guess what? We get that. So here is JR. Why not J? Here's the question number one. Why not just use J here? I mean, I know I need to go back to like 1016. Why not just go say jump back to there? Why can't I just have jump? Why can't some use a jump when it's done rather than JR?
You don't know where it's referring to?
Yeah, because you don't know where it's returning to. You want something to be able to be called from different places. It's right. It's like go sub and return. You go back to wherever you were, right? So already you see some good engineering here where JR is better than J because now I can call some from different places, right? Okay, so that's good. Question 2, that's the answer. Here is what was requested earlier. We didn't like the fact that I had to hard code that 1016 in there. So guess what? I introduced you to something really cool called jump and link. Anybody's flown internationally? Japan Airlines, another acronym here. So what this says is take those two lines, which is like 1008 and 1012, and what this 1016 is the line after the jump, right? Well, JAL sum is done. It does it for me. It says, go grab where I am, 1008, add 4 to it, 1012, stuff it into $RA automatically. Notice, by the way, $RA is not even listed here. It just knows how to do that, which I really am happy with. And you know why I'm happy with that? Because I don't have to specify anything in my bits. Because it always affects RA by default. I know that my set system does. So therefore, this guy can be the J format. There's my 26 bits of target address, and I'm cool. Because I know I'm always changing RA, so this JAL, it does this for me. And the reason we do this is the 2 bullet points. We're going to one of the things you do all the time is functions. Rather than having these 2 instructions, I now saved one. We've seen that before where I kind of have added another MIPS instruction to save me one guy when I do something very often. So that's cool. And the best part about it is there's no more 1016 in there or 1012. I now can have this JAL. I can take that code snippet and go and move it up, and it still works. Wherever it happened to be, it moves down. RA is set. It goes back to wherever the line after the JAL. I love it. Great. So, JAL should really be called LAJ. And it should be called LAJ because it's link and jump. Link means set up the link to come back to where I am. Link in this sense means set up the $RA, and then do the jump. If I say jump first and do the link, it's like, wait, I forgot where I was. It's like, right, let's first take your key, put it in the lock, and then write down where the key. No, you can't put the key in the safe. That doesn't make any sense. So the whole idea of linking first while you're there, where you know where you are with the PC, then you take the jump, and then you can change PC and you're fine. Otherwise, you have to kind of remember where you were. It's annoying, right? So it's really link and jump, but we called it JAL for there. So the cool thing that you now know is JAL and JR are the way you call and get back. That's the most important thing you've learned so far about that piece. So JAL and JR are a pair. They work together. JAL sets the return address up. JR, $RA. JR, by the way, could have any argument. JR has an argument here. JR, in theory, could be written like JAL, where it's you automatically assume that RA is what you're JRing to. But they said to themselves, it would be useful to be able to jump on any register. So they added the idea that you would explicitly specify the 5 bits of what register you want to JR on, and 99.9% of the time, it's always $RA. But that 0.1% is kind of cool because it lets you JR on anything. It lets you basically change the PC based on any register. I could set up $V0 and then JR on $V0, and that could be kind of cool for whatever code you could see that as a possible option for that. That's not usually what compilers put up, but you can now hand do it and do some fun things with that. It's kind of cool. So the question came up here. What's your name again? Christina has a question, which is a great question, which is, wait, that's nice, all well and good, Dan. We can't just go away. What happens if I'm in some subroutine, like here's some square, and I need to call mult? I got to call somebody else. How you explain to me how I go from, main to sum and back to main, but you haven't told me any system that I can go from A to B to C and then back to B, then back to A? Wait, and that sequence can be almost infinitely long. I can make 100 calls, like in what style of programming? Recursion. I'm calling myself over and over. I have to keep remembering where I was. How do I remember that now I'm almost back and now I'm back to the top? How many levels down to go exactly back to the top? So the thing you got to remember is there was a word of what happened when I started to have too many registers I can have for an expression. There was an idea that we had, which was using the big wall. What was that called? Memory. But what was that idea that I used the wall as it was filling the cup and the cup was spilling, right? The cup was spilling. I spill to memory. That's what we're going to do here. We're going to use memory and spill the information to memory. Okay? So now I get to tell you about how memory works. And this is a slide that I usually had earlier, and I felt bad not having it, but it kind of didn't fit in when we were squeezing the semester tighter. We have to zero-sum game for our semester curriculum as well. When we want to add all this awesome parallelism stuff, you got to squeeze the other stuff, right? So that's unfortunate. So a lot of lectures, we didn't drop any single thing, but we just squeezed them together. So it's like a four lecture sequence becomes 3, et cetera, et cetera. This kind of got squeezed out, and now it's kind of about 3 slides. This used to be an entire lecture about how memory works. But it's all relevant exactly right now, which is, you didn't really need to know about how memory works until now. So here's the key. There are 4 different kinds of memory. But for now, there are 3 that affect a programmer. Static, heap, and the stack. Static are things that are globals. Anything that's true for the life of the program. The static memory of a program is never going to change. It is static. Static means not dynamic. It doesn't move. So static is fixed. What memory that you need from a programmer's point of view never changes. That it can't get bigger. A global thing. You've said, I'm making a global array, and it's going to live for the life of the whole program. Put it in static, because it's not going to move and stretch and grow. Okay? How about the heap? The word dynamic. See, look, dynamic says it's not in the static area. And stack is also a dynamic thing. So heap and the stack are both dynamic. But you have a fixed memory. How can you have 2 things which both need to grow and shrink? If I had one thing, like, you ever heard of accordion time, where you say, I have an hour to do something, an hour to do 10 things, and what things need to be done right now? Okay, these first 9, prioritize them. The last one, I could really take all day to do it, or I could read a book. I could take all day, I could use that to squeeze, and that can be accordion time. It could be fill the whole thing or fill nothing. Okay, it's accordion time. The heap is an accordion space, so it'll grow and shrink. The stack is an accordion space, but I have one single linear thing. How can I have 2 accordions in there? How is that possible? How about one guy grows up, and then one guy starts on the top and grows down? And they kind of both share the middle stuff. Great idea. And if the stack needs more of it, then the heap gets less. If the heap grows more of it, needs more of it, then the stack gets less. Isn't that cool? So the heap is dynamic stuff for only and only malloc. Easy. Remember that special malloc thing where that contract where you get the stuff? That's malloc. How about the stack? Well, the stack is basically everything else that's not static and malloc based, which is local variables. It is all the information that you might need when you're making this recursive calls. We call those stack frames. We're going to see a graph about that next time. Okay? So here it is. This is the thing we kind of felt like we designed right now. Bam, you kind of designed it for us. The code part is where the program loads in. So the code lives in your shared space. You didn't know that. You didn't know your code was going to live with you in your data, but it does. And this is why people have had security problems, because the code lives there. If you can take your PC, which is over here, and then move it down there, all of a sudden you're now, I mean, there's obviously a PC, which is the guy, sorry, the PC's down here. If you can have the PC move up here, now all of a sudden you're actually running your data. So you don't want to move PC, but you can actually do that. So that's really fun. We'll see how to do that as well. So code, let's say run the program. Bloop, the code gets loaded in here from 0 to wherever. Then the system figures out how much memory you need. In the static space, all the global stuff, it then says, that's how big your static is. Then it says, here's the line there, and before you make a single call to malloc, it stops it and says, okay, the heap is going to grow from here up. Then it says the stack's going to go from the top down. The stack keeps charge of what procedure is currently running, okay? And all the data, the local variables for that procedure live up there. And they dynamically grow. I'll show you a nice animation on Wednesday. So that's basically the stack, that's the heap, that's the static, and that's code. Any questions about this picture? The first time I've shown it to you, but it's a really important picture that you understand. Yes?
What about like when you have more than one program?
Very good. More than one program, no two programs share the same memory space unless you explicitly say that. This is all yours. So you might have 1 million programs. If you go type top to your system, you'll see all these daemons running and all these other things, 14.5 shells. None of them overwrite the same, what we call virtual address space. So we kind of pretend, we're going to see why it's not true, but how we pretend that each of these programs lives in its own unique, secure memory space. 4 gigs for each program. You say, wait, I have 100 programs running for 400 gigs. I didn't know I had 400. Hey, I got 400 gigs. And wait, I only have a gig of RAM. How's that working? We'll explain how that whole thing works later. But that's a great abstraction. Abstraction, the big idea in this course, that's one of the most powerful abstractions in computer engineering, is the fact that each program thinks they've got the whole thing to themselves, but in fact, they happen to be living with other people, and how that works is really cool. When I finally show you the hood on that part, that's really a huge eye-opening experience for people. But from now on, every program lives independently in their own in their own private space. And we'll talk about how to make that explicit later, to share it if you want to. Yes? Why didn't two spaces grow dynamically? Well, you know that malloc, the more I malloc, the more the heap's growing. And the stack is growing as I make more procedure calls. Every time I make a procedure call, like a nested call, I need more stack zips to remember how to get back. Is it too complex to do this? Well, they're both growing, so why not just have them grow toward each other and share the space rather than have them both?
Why do you need a stack and heap? Why can't you just have one?
Why couldn't you do it all in, say, the stack or something? Well, you want to be able to have, remember the stack is basically a function, the stack grows as a function of your recursion level and how deep you are in some nested call chain. That's the basic stack and all the local variables about that stuff. Including, by the way, a dynamic array. If I say, int a of 20,000, that is eaten up by the stack, different than malloc. So that's a different place. And that could go away. When that subroutine returns, that goes away. I'll show you how that works. It's a, we call it a stack because it is a stack idea. You stack plates up and they go down. So that's the kind of thing. But you look at it from this side up. It's like a stack. It's like a stack upside down. Yeah. Yeah, I mean, you could have with more complexity, but it's cleaner to kind of divide them up to the part that grows based on function calls and the part that grows based on malloc, the explicit request from memory. It's cleaner that way. Yes? Yeah, the heap, correct. How about this? How clever. Let's all pat ourselves on the back for calling a stack, but wait, why is that a heap? It's not a heap, right? In the data structure term of a heap, it's not a heap, which is the tree-based thing that the top guy is always the biggest. It's not a heap. It's another stack. It's exactly right. So we kind of have to, we pat ourselves with one hand and then shoot ourselves with the other hand, which is like ridiculous. That shouldn't be called a heap. It should be called the malloc stack and the procedure stack is what I would have called it if I were designing this thing. Yes, Brennan.
What about static variables that live inside functions?
Static variables that live inside functions, they cannot live inside functions. They can be referenced inside functions. They can live in there, but the room is made for them down here. So you can have, by the way, so for example, if you want to have a foo procedure, count how many times it's called, you can say static int times I'm called equals 0. Times I'm called equals 0, reset it to 0. It's going to live down there, which is why it has persistence. As I call it, every time I'm called, I say times I'm called plus equals 1, plus plus. And it actually, remember, over the life of the program, how many times it's called, but how is that possible? But it's in stack. It gets thrown away when you, no. Because I said the word static, it actually makes room for it down there, and that's why it works. It's so cool. So if it's inside of a local function, it puts it, if you have the word prefix static for it, it puts it down there, so that way it always lives. Yes?
So is the memory allocated during compile time or runtime?
We'll talk about when it is compiling, assembling, linking, and loading. Compiling, assembling, linking is the process of making the cal part, making the executable. Loading is the process of running the program, so it's during the load time.
In that case, how do you know?
Which is here. Load time says set this all up and go. That's what load time does. Okay? Good. Okay, so let's actually use it. 20 minutes, and I'm on time. Good. Everything's good so far. Great. By the way, great questions so far, guys. This has been really dynamic. Good day. Because I think all the questions have been answered, and they were important questions. So here's the key thing. You have access to SP, which is another. Well, I haven't showed you yet. It's another one of the registers, other than the 32. And SP tells you where the. Oh, did I show this picture? Right there. I didn't show you this picture. I didn't say that. This is the stack pointer. You want more memory? Take SP and make it smaller. That's yours. You control it. You know how fast it was to do that? Instantaneous. One cycle. SP equals S, virtually, right? Here's the comment. SP equals SP minus 4. There's another integer for free. There's another 4 bytes for free. SP equals SP minus 1,000,000. Bam, 1,000,000 bytes for free. One instruction, one clock cycle. Love it. Love it. So that's fast. Malloc is slow. Malloc could be really slow. Malloc is this dynamic space where it has to look at all of its range. It has to guarantee a free array. So it has to look into all the tables to know how big you ask for, look for all the space it has. It might get really complicated. You heard of fragmentation, where you remember it gets really fragmented by asking for a space and freeing it up. I'll show you a slide that explains that. So that could be slow. Malloc can be slow. Static allocation, immediate. Immediate. Malloc has a great test. Malloc can tell you when it fails. What does Malloc do when it fails? It says, hey, I want 1,000,000 bytes. It says, I'm sorry. I went to the cupboard's dry. I can't give you 1,000,000 bytes. What does Malloc do? Yeah, it has a nice handshake where Malloc returns a 0 to you and you're all cool, right? You are down at the level of changing your stack. SP equals SP minus 1,000,000. You actually might have that fail. Is that clean? How is it going to fail? It fails because you're going to be in some subroutine called foo, and you're going to have a local array that says, make a local array A of 1,000,000. And when you translate that C of array of 1,000,000, int A of 1,000,000, inside of foo, subroutine, you translate it to MIPS. What is it MIPS? Literally, add I, SP, SP minus 1,000,000. Now, you had the top of the heap, and you just explicitly took the top of the SP stack pointer, and maybe moved it past where the heap is. The system will check that. But can you, as a programmer, check that? No. Where's the return value on int A of 1,000,000? Give me some love. Ain't nothing there, my friend. Int A of 1,000,000 will just go crash, bad, bad, bad. So this has been one of the subtleties we didn't talk about of whether you should use malloc or whether you should use this dynamic arrays in your C code. If you use malloc, you have the wonderfulness of calling for malloc. Malloc returns null. You say, I got no space. You tell the user, I'm so sorry, sir. You've asked for space, but I couldn't get it for you. I'm gracefully exiting. Okay. Now, you're in int A of 1,000,000. How do you, as a programmer, try to gracefully exit out of that? You don't. That line itself crashes. No way to check that. So that's a really strong subtlety between using dynamic arrays and using malloc. Malloc, if you use them like crazy, you're fine. How about int a of 1? That certainly isn't a problem, is it? It can be. Because what if the heap is just crawled up to there and int a of 1 goes past that? Again, a crash. So any dynamic array can be a problem. Forget dynamic array. Int a, int x can cause a problem. Who's ever seen that problem? What happens if you have a recursive guy that just runs off, that doesn't have a base case that's correct? What do you get? Ha ha ha, say it louder. All together, 1, 2, 3. Stack overflow. You've always wondered what it meant. Ha 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 ha. You now know what it means. What does it mean? Tell me now in 61C, like the whole light has come to you, understand it language. It means your stack pointer has been moved down and down and down with all your recursive stack frames until it crossed the top of the heap line. Done. Stack overflow. You can't just have recursion go on forever, because unless it's tail recursive and done cleverly, and I'll show you what that is. But if it's embedded recursion, we have to remember something, right? Then you can't do it. We'll talk about tail versus embedded in a second, how it reflects to here. But let's keep moving on. So we're now here. SP is the key thing that you can now affect. You can move the stack pointer explicitly, but it's dangerous, right? If you're hand coding MIPS, or if you're trying to think of this as a C thing, we're using a dynamic arrays. So, sum square is going to call mult. How do we make this happen in 15 minutes? Ready? Go. Here's the code. Let's see. Let's think about this. How many slides I got to my peer instruction here? How are we doing so far? 1, 2, 3. Okay, good. We can make it happen. Good. So here's sum square calls mult. So first, this is the meta idea of how you make this work with nested calls. And this is true for recursive calls also, you can imagine. First, I'm going to make room for two things. Why? If sum square is going to be calling mult, what is available to sum square? Right there, the first line. Sum square, yellow line, sum square. What's now available to sum square based on the register calling conventions we said before? Go. I know A0 has my X, A1 has my Y, and RA has wherever I have to go back when I'm done, right? Which I do with my $RA. Okay. Now, I'm in sum square. I'm hand authoring sum square. I somehow have to call mult. Mult takes X and X, which is A0 and A1, X and X. I have X and Y in my A0 and A1. What's the first thing I have? So what am I probably going to be doing? Probably clobbering my A1 with an X, so I can have my X and X to do my jowl on my mult. When I write a jowl on my mult, what's going to happen to my RA? What happens to the good RA, which is the way I got the pointer I used to get back? What's gone to when I call a jowl on mult, what happens to the RA? Immediately clobbered. I no longer have a way to get back home. Right? My popcorn trail has been eaten up by the birds. Okay? So, my job as sum square, I have to remember RA to get back to main, or whoever called me. So I got to store RA. What else do I need to store? Maybe or maybe not. I haven't told you what the convention is of Y. Couldn't I just, you think Y, right? Because I need Y later, by the way, first of all. Couldn't I just store Y in, I don't know, I'm kind of being sneaky here. How about A2? Look at mult. Mult only uses A0 and A1. Why can't I just put Y to A2? Because, get louder. Yeah, what if mult, in doing its job, calls somebody else? I also don't know how mult is written. I mean, I kind of think I know how mult is written, but maybe mult decides to use A2 as like a scratch space or something. So there has to be an agreement for what is preserved across a call and what is not. That has to be understood. And I haven't told you that rules. Those rules happen on Wednesday. But I will tell you that A's are volatile, which means I can't use A2 as a scratch space because mult, as my child, has full rights to clobber all over everything I had. Okay? So I can't use that. So I need to store my Y, which is my A1. So I'm going to store both the Y and my $RA. So I'm going to take the SP and say SP equals SP minus 8, or add I SP minus 8, and boom, boom. Now I have two words for free. And I store my RA there, and I store my, look, my A1, my Y. Now it's stored there. And SP is at the bottom of this guy, okay? So now, here's what happens. I say, what do I do next? Sorry. I set up my second argument to mult, right? I say the A1 equals A0, so now I have X and S, and now I jowl mult. So far, I'm good on this one, right? And now I come back, and now, here's the key question. What do you think is the agreement about add on SP? Can add change SP? I hear you. I say yes. It can move it around, but when add's all done and comes back to me, when I'm back at this line below the jowl, what's better be the case for SP? It better be where I left it. From my point of view, from abstractly, it better not be changed. It's like it's kind of like you give your house to your friends and they might trash it, but when you come back, it looks the same. It's like risky business. It's like, oh, you didn't mess with it there. That's nice. Turns out they trashed it and then they bought all new stuff and you can't tell. Abstractly, you can't tell. Same thing here, right? They can mess with all they want to, just that there has to be agreement that they better not change it when I come back. So when they JR to come back to me, SP better be the same. Why? What if SP's changed? What does this mean anymore? What does LWA1 0SP mean anymore? It's garbage, right? If they don't, it's like those two pointers, which are kind of the virtual pointers to like where I stored ret and y. If they move if all of a sudden somebody takes the treasure island, they have the little X where there's treasures. If they pick that up and move it over here, it doesn't mean anything. I'll dig in the hole and there's no more gold. I can't have that. I can't have SP move because SP is my big X in the sand telling me as a pirate, where to get my Y and my RA back, right? So now I restore. By the way, LW this is the phrase restore. I restored Y is. Now Y is back where Y is. And V0 is now, remember the agreement better be to fill V0. When I jowl somebody, if it's not a void, you better fill V0 or optionally V1 if it's a doubly thing with the value. So now V0 is filled. So my job was to say return mult x plus y. This value, mult x is now V0, because that was the job of mult, is to fill V0. So look what? Add V0 to V0 plus A1, which is mult plus y, right? Because y is now restored. This is one of the consequences of having to have all operations operate only on registers. Ideally, I'd be able to say add V0, $0 SP, but I can't do that. I cannot do both a memory access and a calculation at the same time. That's one of the things about our architecture. You have to either have move back and forth memory or do something. I can't do both, because you kind of want to do both here to save your line. Then I restore $RA, and now I fix the stack. Why do I have to fix the stack? The same argument for my caller. They might have used the stack in a usable place. I got to restore the stack. So first line is I change the stack, I better restore it like that. They're called bookends. If I always put it here, I put it at the end, and now by the time, from my point of view, the stack hasn't changed. Point of view of my caller, stack hasn't changed. Is that nice? Okay. And then JR$RA. Yes, question. Great question. How does the compiler know? That's a very good question. How does a hand author, how would you hand authoring this know? Because I kind of start working on it as two things. You could do what some people always say, which is just store all the S's and T's and A's. Just kind of store all 32, restore the state. That's really annoying, because every visit memory is a slow walk. So I want to have to spill the fewest number of things. How do I know? It's based on the usage of it. It's based on a kind of a complicated process of, well, okay, I need that when I do this. Or there's a boilerplate template, which is any function, you kind of store your RA first, and then you store whatever things you're going to need in the process of doing it. And that'll come out of doing it. That'll come out. Okay. Can I get around doing this? If I didn't have Y in the expression, I wouldn't need it to restore Y. So you kind of learn that by looking what's needed based on that. Okay? So far? It's kind of fun. Question in the back, yes. If you're in the back, you got to wave your hand because I can't see it. Yes. How do we do static variables? We'll talk about that. We'll say that one. That's good. That's a good question. Yes. I can't. I'm so sorry. Shh. Louder. Yeah, okay. Oh, I see, yeah. What you're doing is you're bloating the size of my code, and you're saying, rather than doing the 8 here and the 8 here, just like have a 4 every time you use it, and then have a 4 every time you restore it. And then you could do that, but now you have more lines and it's slower. Your program is now slower than mine, so not so good. I mean, in general, right? I mean, right? You've taken one line and made it 2, or take one line and made it 20, and that's not so good. Okay, let's see how we're doing for time. Okay, so here's a steps or procedure call. Now that I've spent so much time on that one, it's a little bit faster for the last part, which is save the guys on the stack, assign the arguments, if any, do a jowl, restore the values. That's a procedure call. Here's the rules, which say that the args are in A's. What's your guess now if my args are more than 4? Yeah, they're in the stack. You got to put them in the stack and then do that. That's just kind of a general thing, right? You've seen that already. Return of V0, register conventions. Register conventions are all about what Wednesday's talk is. So here's the basic structure. Here's my entry label. Here's my first. I make room on the stack for whatever the frame is. These are called stack frames. Everything part of a procedure is the stack frame. I then store the RA first, which is going to live on the top of that guy, which is the frame size minus 4. It's the top of that guy. And then as I grow, I save more things I needed to. You saw that I needed A1 in the last guy. Here's my body. I call all the guys. If I want to, I might do some jowls in here, but that's fine. And then as long as I have this as the bottom part here, restore other things if I need to, and then I load back, I restore RA, I fix the frame, I fix the stack back to wherever it was before. Notice that these are all bookends here. You see that nicely there? Prologue, epilogue are bookends, and then the jr.ra. Now you've seen almost all the registers. It's starting to become really clear how stuff works now. This is really awesome. I'm going to give you 2 more T's. We ended up having 2 left over after doing all the things we needed to do. And they said, you know, they're not contiguous. They're like over here and then here. But give them more T variables because it's nice to have more scratch space. So that makes it easy for the compiler. Compiler authors are saying, thank you so much. I needed that. That's so great. So they're very happy. As a hand authorer of MIPS code, you're probably also happy. You know about the A's, the SP, the RA. The guys that are in the white, you don't need that. They're in this slide. You're not going to need those guys. AT, we'll actually see how AT works ourselves. The other guys you don't need, no need to worry about them, but you can read about them if you want to. Peer instruction, if I can get this in. Yes, let's hit it. So, this is one of the best questions, I think, in terms of peer instruction in the past years. I love this one. So, I probably need to move this so you can see. Here's factorial written written the standard way. You've seen it a million times. And I want to know is, could you, this is a recursive guy, right? Could you copy A0 to A1 and then not store A0 as I do other recursive guys? Just use A1 as my scratch space and use to remember what my current n is, right? Because you see that I need n. After I call this recursive guy, I still need n after I'm done. Could I just store it in A1? Is it true that you have to store A0 on the stack? And is it true that you also have to store RA on the stack? Okay? So here's the true and false, 8 possible options. The olden days we had clickers that had 8, like a number key, and now I just have 5, so I have to kind of combine them a little bit. But how are we doing here? Yes?
Are we the compiler or assembly program?
You are the compiler. Okay? Which produces, compiler guy is the guy producing assembly, so you're the guy producing assembly. So what assembly do you do? Okay? And unfortunately, we're out of time for discussion. And also, this is a really fun one. So the discussion actually isn't so critical in this one, actually. And I do have to run to an exam right after this, so unfortunately, let's save questions if we can until Wednesday. Hopefully nothing critical will come up. Okay, let's get to 188. All right. Here we go. Come on, vote in. Okay, so you're still voting as I'm stopping it. All right, what do you think the answer is, folks? I only have, so let's see. Let's see the display here. Okay, so could you copy A0 to A1? What do you guys think? No, we kind of talked about that because the next time I couldn't just keep overwriting A1, so that's, the first one's false. So I'm kind of A, B, or C here. Must I save A0 or RA? Must I say? Most people say, yeah, you got to save it. There's no way to get around it. What if I were smart as a compiler author, looked at this thing and said, you know, This is just factorial. Why not write iterative factorial? Nothing stops the compiler from doing that. If it's iterative factorial, there's no recursion anymore. Just have a little loop, little thing, way faster, no stack frame, no RAs, no memory access. Love it. And the answer is A. Love it. How about that? And that's an important thing you guys know, that compiler authors have full flexibility to rewrite your code the way they want to, and it might change the behavior you think it is. That's really important. Okay? Thanks, folks. I got you. Woo-hoo!